of the IIR filter using the Butterworth approximation. So far, we have discussed the different concepts which are used in order to design the filter, that is known as the filter design approaches. In these discussions, we have discussed that during the time of the designing of the filter or to derive the realization of the filter, first step is to define the specification, in which we define the pass band, stop band optimization criteria. And in the second step, we decide what is the design method, that is whether we are interested for the FIR filter or the IIR filter. Then in the third step, we consider here what is the realization which has to be used using the block diagram representation or the signal flow graph representation, or sometimes we also use that here the dependence graph or data flow graph. And we have discussed so many structures like the direct form 1, direct form 2, parallel form, cascade form, and lattice realization. And then the fourth step is the implementation. If we have achieved the satisfactory results in these three steps one by one, then we will move towards the implementation of the filter. That is the fourth step, and we can implement our concept using the software approach or the hardware approach. Now, here we will see that the implemented filters performance is not exactly same as we have designed it. So we will find that there is some deviation after the implementation. So what we have to do, we have to analyze and we have to make a comparison between the performances of the implemented filter and the design filter, and also we have to analyze what is the range of the deviation in these two types of the filter, that is the implemented filter and the design filter. In the FIR filters, we have discussed that this is the linear phase FIR filter, and we can design it by using the optimization method, windowing methods. And in the IIR case, we can use the pole 0 for the description of the stability and its criteria, and we can design here the IIR filter using the optimization approach, or we can use one method, that is the first filter will be designed in analog domain and then it will be transferred into the digital domain. And in the analog domain, we can here use any one type of the approximation like the Butterworth approximation, Chebyshev 1 and Chebyshev 2, as well as the elliptic approximation here. And today we will discuss here in this concept of the analog approach, that is the filter will be designed in the analog domain. Then we will discuss how the design filter will be transformed into the digital domain, and for that purpose we will utilize here the Butterworth approximation. But before going into the domain of the designing of the IIR filter, we will summarize here the some concepts of the FIR filter. That FIR filter is the finite impulse response filter, and its transfer function is represented by this polynomial here, that is the Vz B1 z to power minus 1 plus and so on up to the Bn z to power minus n, where n is the order of the filter here. Or we can say it is described by a polynomial Bz divided by z to power minus z to power n. And it is also known as the moving average filter, or the MA, and there are the n poles at the origin, that is the z is equal to 0, hence guaranteed stability. There is no question of the instability here, and there will be the n zeros, that is the zeros of the Bz. That's why this is also known as the all zero filter. So it corresponds to a difference equation, that is the Yk will become here the B0 Uk is the input, or sometimes we can write it the Xk plus B1 Uk minus 1, or the Xk minus 1, and so on up to the last coefficient, that is the Vn Xk minus n, or the Uk n minus 1. Here the impulse response of this FIR filter will become the coefficients, that is the V0 will become the H0, and H1 will become the B1, and the Hn will become the Bn Hn plus 1, and other values, these values will become here the 0. So this is a summary of the FIR filter which we have discussed so far. And if we see here the designing of the FIR filter, that is the here the symmetric impulse response, that is the non-causal or the anti-causal zero phase filter, then we can say it exists towards the left side and the right side of the here the n or the k is equal to 0, and this filter have the coefficients of the h minus l to the up to the h plus h l here, including the h0. That is, it is distributed towards the right side and the left side of the h0, having a length of the l. And the frequency response of this filter will become naturally e to power plus jx plus e to power minus jx. That will become here the 2 cos x here. Or e to power, if we represent it into the frequency domain, this can be represented as summation of the hk e to power minus j omega k, or sometimes we write here the some coefficient ak, bk, or the dk multiplied by the cos omega k. And this is a real value function here, or we can say there is no concept of the angle, so the zero phase transfer function is this one here, that belongs to this category of the FIR filter, that is the non-causal zero phase filter here. Now we are interested, in order to design the causal filter, then naturally there is a need of the transformation, that is the negative coefficients will be transferred toward the right side, or they will be truncated here. So here the causal linear phase filters can be said as the non-causal zero phase plus some delay here. Due to the delay, what are the negative coefficients, they will be shifted towards the right side here. So we can say now the coefficients are starting from h0 to h of the n, where the n will be the order of the filter and n is equal to 2l, that is, say it is the even here. Then frequency response will be represented something like in this manner, that is the h e j omega, and that is coefficient hk multiplied by e to power minus j omega k. And now if we see, then find this is a causal implementation of the zero phase filter by introducing a group delay. And what is the group delay? That is the z to power minus l, where the we have used z is equal to e to power j omega, then it will become e to power minus j omega l. That is the same which we have described in the previous slide, but multiplied by e to power minus j omega l. That is, the if this is multiplied by e to power minus j omega l, then this will be a linear phase FIR causal filter here. Now if we discuss here the symmetricity and the linear phase conditions, then we'll find that here the order of the n may be even or the odd, and at the same time the symmetricity may be the symmetric condition, or that may be the anti-symmetric here. So if we consider here the condition, that is the order of the filter is even and it is symmetric, then it is named as the type 1 linear phase FIR filter. And in this case, what is the specialty? That hk will be equal to the hn minus k, and e to power here the filter's response, that is the hz will be h omega will be represented by this equation, that is the h e to power minus j omega n by 2, and multiplied by dk summation k equal to 0 to n dk cos omega k here. And this is suitable to design the low pass filter, high pass filter, and the band pass filter. Similarly, the type 2 that has the order of the filter is odd and it is symmetric, it is suitable for the low pass filter and the band pass filter here, because the zeros will be at pi here, so this will be suitable only for the low pass and the band pass filter here. The type 3, that is again the order is the 2l, but the 2l is the even here, and it is anti-symmetric, and at that time here the zeros will be at 0, omega is equal to 0 and pi, so it will be suitable only for the band pass filter. Similarly, if we consider the type 4 symmetricity, or the type 4 linear phase FIR filter, that is defined as having the order of the n odd and the nature is the anti-symmetric, then it has the 0 at omega is equal to 0, and it will be suitable for the high pass filter. This is the some concepts or the summary which we have discussed here related to the FIR filter. And we know that during the time of the designing of the FIR filter, we define what is the value of the pass band ripple, and what is the pass band edge frequency, what is the stop band edge frequency, and what are the values of the ripples in the stop band. And now we are moving to the next domain, that is the designing of the IIR filter. In IIR filter, we know there will be the polynomials, that is the Bz divided by Az, when we are interested in order to describe the transfer function of the IIR filter. IIR has the feedback. So here this may be described using the here the polynomials of the Z in the numerator as well as in the denominator. and this may be described as the b0 z to power n plus b1 z to power n minus 1 up to so on, up to the last value. Say this is the bn z to the power minus n. Similarly, the denominator will be described as z to the power n plus a1 z to the power n minus 1 and so on. The last value will become here the an having the z to the power 0, or this can be also represented here something like in this manner, that is the b0 b1 z to the power minus 1 and so on, bn z to the power minus n divided by 1 plus a1 z to the power minus 1 plus so on up to the an z to the power minus n. That is, this is a ratio of the two polynomials. Either we can describe it with the help of the z or z to the power minus 1 or z to the power minus k, and we know that representing the transfer function in z to the power minus k is better for the purpose of the representation of the DSP algorithm. That's why we have represented here the second term. Now n is the poles are the zeros of the AZ and n are the zeros of the BZ here. Infinitely long impulse response we will get in this case, that is the infinite impulse response. And there is a question of the stability. The system, this type of the filter may be stable or unstable, and it will be stable only if this condition is fulfilled, that is the all the poles are lie inside the unit circle. Since there is a feedback, so here the instability may take place, and this type of the filter will be only stable when all poles are light inside the unit circle. And now the corresponding difference equation may be represented something like in this manner, that is that left side we will consider here the y case, and towards the right side we consider here the x case or the u case, or we can represent this one is something like in this manner, that is the y k equal to b naught u k or the x k plus b1 u k minus 1 or the x k minus 1, and we have described it in previous lectures. And we will find that this term, that is the having the input terms here, that is the x k or the u case, this is known as the moving average. And the second term related to the y case, that is the here the previous output, this is known as the autoregressive, and in total we will call it the autoregressive moving average model or the filter or the system here. Now, what are the advantages of the IIR filter? For the same specification or in order to get the same performance, the lower order we will have to maintain, that is the low order filter can produce sharp frequency response, and low computational cost will be there because of the lower complexity here. But there are some disadvantages which are associated with the IIR filter, because the designing is difficult and stability. There is a question on the stability. Stability should be checked or the guaranteed. Means it is not always we can say that the IIR filter will be stable. So we have to check the stability in this case. Phase response and not easily controlled. No linear phase FIR filter can be designed here. And here the coefficients sensitivity, that is with the change of the parameters, the coefficient sensitivity will take place, and quantization error and the finite word length error will take place in this case here. Now there are so many methods of the designing of the IIR filter. That is, the first one is the weighted least squares design method, and the second one is the minimax design method. And here we will discuss this method. That is, first we will discuss how the IIR filter will be designed in analog domain, and then how it will be transformed into the digital domain. Now see here, if we consider here the Butterworth approximation, then Butterworth approximation GS is nothing but that is a multiplication of the HS multiplied by H by the minus of the S, that is the HS square, and this can be written as the 1 upon 1 plus minus S square divided by omega C square its whole power n. Or we can say G J omega, or the square of the S J omega, it will become 1 upon 1 plus omega by omega C its power twice of the n. Or we can say here the poles of the HS are lying towards the left side of this circle here, and poles of the H of the minus S are lying towards the right side of the circle here. And we also know, as we are increasing the order of the n, we are approaching towards the ideal value of the filter here. We have discussed this one in the previous slides or the previous lectures. Now, commonly used analog filters are the first one is the Butterworth approximation, that has the smooth curve in the pass band as well as in the stop band, and the next one is the Chebyshev, having the two categories, Chebyshev 1 and the Chebyshev 2. In the Chebyshev 1, there are the ripples in the pass band, and the transfer function of this one, that is the h j omega square. This may be written something like in this manner, that is 1 upon 1 plus epsilon square Tn square omega by omega c, where the Tn is a polynomial, and this is named as the Chebyshev polynomial, and epsilon is related to the pass band ripple, which we have described in the previous lectures. And the function, this polynomial, that is the Chebyshev polynomials, may be described something like in this manner, that is the T naught x. This is where the n will be 0, it will be 1, and when the n is equal to 1, this will be equal to the variable itself, that is if this is a T1x, then this will become the x, and T2x, that is the n is 2, this will become the 2x square minus 1, and in general, for the nth value of the this one, that is the Tnx Chebyshev polynomial value, this may be described as the 2x times Tn minus 1x minus Tn minus 2x. Now, the Chebyshev, what as we have discussed, that the Chebyshev Butterworth has the smooth curve, but the Chebyshev 1 has equal ripple in the pass band and monotone in the stop band. And low pass Chebyshev type 2, it has the pole 0 it is also pole 0 filter based on the Chebyshev polynomial, and but it has the monotone in the pass band and equal ripples in the stop band. Elliptic has the equal ripples in the pass band and stop band both. So what is the gain of this one? We will get here the transition band is smaller, and we will yield here the smaller order for given set of the specification here. Now, if we have designed any filter, suppose we have designed a filter having that is the low pass filter, and we are interested to transfer that filter having the another cut of the frequency, or we are interested to transfer the filter towards the high pass or the band pass, band reject, etc. Then how the frequency transformation will take place? For that purpose, we will develop a prototype low pass filter having the cutoff frequency of the 1 radian per second, and then it is transformed to the properly scaled low pass, high pass, band stop, or a particular range of the cutoff frequency here. For example, if we replace s by omega c, it means the designed filter will move to having a cutoff frequency of the omega c. Similarly, if we replace s by omega c by s, then it will turn in low pass filter into the high pass filter with cutoff frequency of the omega c. And if we replace the s by s square plus omega 1 multiplied by omega 2 divided by s omega 2 minus omega 1, then we will turn low pass filter into the band pass filter. These are the frequency transformation which will be used in order to transform the design filter towards the high pass filter, band reject filter, or towards a new filter having the another cutoff frequency. So first of all, we will design the low pass filter, and then accordingly, as per our need or the requirement, we will transform this design filter as per the given specifications. Now, this is the approach, that is the first, the filter will be designed in the analog domain, then conversion will take place as per the requirement here. And during the time of the conversion, we have to see whatever the stability domain, that is whatever the pole, if the poles are lying in the left half of the S plane, then they should lie inside the unit circle here, and accordingly we will transform them. And there are the different conversion methods, and for example, we can use here the inverse impulse method, or we can use here the bilinear transformation. Now we can use here the different types of the MATLAB command for the purpose of the designing. Here we are just going to describe in details how the IIR filter will be designed in analog domain using the Butterworth approximation. then how it will be transformed into the digital domain. As we know, Butterworth approximation has the flat response in the passband, and its magnitude square is represented by 1 upon 1 plus omega by omega c, its power twice of the n. And we can say it is nothing but this is the HAS multiplied by HA of the minus S. A means analog here. We are using the HAS, that is the transfer function of the analog filter here. And this will be described as 1 upon 1 plus minus S square upon omega C square, its whole power of the n here. If we find here the roots of this one, that is the denominator term here, then we will find that minus S square upon omega C square, this will become minus 1, its power 1 by n. And after some manipulation, that is, we will get here the S square is equal to minus 1, its power omega is omega c, it's multiplied by omega c square, then e to power j 2k plus 1 pi by n. This is the value of the S square. And when we consider the here the under root of this one, that is the taking the square root of the this S square, we will get here the poles, here the pKs, that is poles associated with the transfer function, and that will be defined as something like in this manner, that is this will become here the plus omega c e to power j n plus 2k plus 1 pi divided by twice of n. This, remember this one, that is this is the formula in order to get the roots or the poles of the Butterworth function here. This equation gives the pole position of the HS and the H of the minus S both here. That is, there will be the double poles here. So, and frequency characteristics, we have described the frequency characteristics that, and we know that as we are increasing the order of the filter here, we are approaching towards the ideal response or the ideal concept. These are the representation here, and we know that the AP is the attenuation in the pass band, AS is the attenuation in the stop band, and in the pass band something we call it the maximum attenuation in the pass band, and AS is also called as the minimum attenuation in the stop band. Omega P is the pass band edge frequency, omega is the stop band edge frequency here. Now, if we consider the previous equation and if we see, then we'll find that AP square is nothing when the omega becomes the omega P. So 1 upon 1 plus omega P upon omega C, it's whole power twice of the n. It is greater or equal to the AP square. Similarly, when omega is replaced by omega C, at that time it becomes the less or equal to the AS square, because this is the minimum attenuation and this is the maximum attenuation. So here we can solve this one here, that is the what will be the value of the omega C, omega P by omega C from this equation, and what will be the value of the omega S upon omega C from this equation. So we have represented these values here, and then we can get here the what will be the value of the omega S, and after solving this one, we can get here the value of the n, and n will become here the 0.5 or 1 by 2 log 1 upon S AS square minus 1 upon 1 upon AP square minus of 1 divided by log omega S by omega P, and this has also been described in the previous lecture. So this is the derivation how we will derive the value of the n. So if the omega P, omega S, AP, AS are given, then from this equation we can get here the order of the filter, and the order of the filter must be integer. So if there is any fractional value, then we will select this one at the next higher value here. So here we will get the final value of the n is equal to 0.5 log. In the logarithmic terms, we can describe this one in terms of the AS, that is the 10 to power 0.1 AS upon 10 to power 0.1 AP minus 1, and in total divided by log omega S by omega P here. Now, suppose we are interested, we are just moving to the designing. So far, whatever we have discussed, these concepts has already been discussed in the previous slide or the previous lectures, and now we are moving towards the example of the designing of a Butterworth filter in analog domain, and in which we are using here the Butterworth approximation. Suppose this is the specification given here, in which what is the specification, that is the pass band. This is a low pass filter which has to be designed, and the pass band attenuation is 0.89125. Stop band attenuation is given here from the graph or the mathematical representation, that is the AS is 0.17783, and pass band ripple is pass band edge frequency is 0.2 pi, stop band edge frequency is 0.3 pi. So these specifications are in the digital domain, that is the frequencies are defined in the digital domain, and we are interested in order to design the filter here. And what is our approach? That first the filter will be designed in the analog domain, and then the designed filter will be transformed into the digital domain here. Now see what we have to do. In the first step, we will convert the specification to equivalent analog frequency, because the frequencies are given here in the digital domain. So we will transform them into the analog domain, and here the by using this approach, there are the different approaches like the bilinear transformation or the impulse invariance method. Suppose we are using the impulse invariance method, then in that one we have to use the omega is equal to capital omega t, and from here we can derive that capital omega is equal to 2 by t tan omega by 2, and this is this capital omega is 2 by t tan omega by 2. This is suitable for the bilinear transformation. So suppose we are using here the bilinear transformation in order to convert the digital frequency into the analog frequency, and if the TS, that is the sampling time period, is not given, then we will consider it as equal to the 1 here. So here the what is the HA omega? It is greater or equal to the 0.89125 for the omega which is less than 0.2 pi by t. Similarly, we can define this one, that is the mod of the HA omega is less or equal to 0.17783 when it passes this frequency, that is the omega is greater or equal to the 0.3 pi by t. See here the specification in this one here. So after this one, the magnitude is below this value, that is the 0.17783, and here before this one, this frequency, the value is greater than this value here, that is the 0.89125. Again, coming to this one here, in the first, after defining the frequency in the analog domain, the next step is to determine the order of the filter. And how the order of the filter will be determined? We have discussed that in order to get the order of the filter, we will utilize the values of the AS, AP, that is the attenuation in the pass band, attenuation in the stop band, pass band is frequency, and the stop band is frequency. And using this formula here, that is the log 1 upon AS square minus of 1 divided by 1 plus 1 upon AP square minus 1, and its total divided by log omega s by omega p. And if we put here all the values, then we will calculate and find that n is equal to 5.88. So what is the next step? The order of the filter should be integer. So we will consider here the next higher integer, that is the 6. So the value of the n is here the 6 here. So in these two steps, in the first step we have defined the analog frequencies, and then we have derived the order of the filter. Next step is to determine the omega c, that is known as the -3 dB attenuation frequency, cutoff frequency here. And this can be derived by their formula which we have derived from the given specification of the Butterworth, that is omega p upon 1 upon AP square minus of 1, and its whole power, that is the denominator's whole power, is 1 upon twice of the n. This can be derived from the Butterworth approximation, which we have discussed in the first equation here. So by putting the values of the n, AP, and omega p, we can derive here the value of the cutoff frequency of omega c, and it is 0.7032. And the fourth step is to find out the poles of the analog filter system function. So here the poles of the analog system filters can be derived from this one, that is the here the as n is 6, the value of the k is 0, 1, 2, 3, 4, 5 up to the 5, right? So here the order is 6. So for the different values of the here the k. And what is the k? K is nothing but it is starting from 0 to n minus 1. We have to derive the pk's. Pk's means here the poles, and we have derived this one in the previous slide here. Just coming to this one, see here we have described this one, how the pk will be derived. Pkb is equal to the plus omega c multiplied by e to power j n plus 2k plus 1 multiplied by pi and divided by twice of the n. So using this concept here, we will derive the pk's for the different values of the k here. And what are the different values? These values are starting from 0 to 5 here. So when the k is equal to 0, we will calculate the pk, that will become the p0, and this is the value here. And as we know, this value has the real and imaginary portion. So we have the two roots here. One is related to the hs and the second related to the h of the minus s. Similarly, we will derive here the up to the 0 to 5 here. And so we will get here the 12 roots here. In place of the 6, we are getting here the 12 because we have considered the hs multiplied by the h of the minus s. So which poles, which roots will be considered here during the time of the designing? We have to keep the concept of the stability during the time of the designing of the FIR filter, and while the filter will be stable if the roots are lying in the left half of the S plane. So we will consider only those roots, those here the roots of the S which are lying towards the left half of the S plane. Hence we will get here the 6 roots which are lying towards the left half of the S plane. These are the roots which are lying towards the left half of the S plane, and these will be considered for the purpose of the designing of the filter. We are getting here the S1, S2, S3, and at the same time they are conjugated, that is the S1 star, S2, and S3 star. Now HAS, this will be nothing but the S minus here the denominator terms, that is the it is the S minus S1 multiplied by S minus S1 star, and S minus S2, S minus S2 star, S minus S3, S minus S3 star, and in the numerator there will be the omega c, its power n. And what is the n? N is the 6. So we have derived the value of the omega c, and we know the value of the S1, S1 star, S2, S2 star, S3, S3 star. Now their complex values. So we will put those values here and we will solve the equation, and finally we will get here the transfer function HAS. Now if we have derived the transfer function, what is the meaning of this one? It means if we have derived transfer function of any system, it means we have designed that system. Since this transfer function is a function of the S, and S means it is a transformation of the differential equation into the complex frequency domain. It means now we have designed the frequency in which domain? Analog domain. HAS is nothing but is the design and transfer function of the system which has to be designed in the analog domain. So HAS is the here the system function in the analog frequency, and after some manipulation we will get here the this representation of the HAS. Now see here, to determine this here the system function, digital system function. What is the next step? We will utilize here the bilinear transformation or any other type of the transformation in order to transform the HS into the HZ. And what is the specialty of the transformation? During the time of the here the finding a relation between the S and Z, we had to maintain this concept that the system should be stable in the S domain as well as in the Z domain. So accordingly we will derive a formula, and according to that formula we will transform the HS into the HZ. That is how the S will be replaced here. And after this replacement of the S, we will get here the H of the Z. Now that H of the Z, that is the transfer function of the filter in digital domain. Now that can be represented using the cascade form realization or the parallel form realization, because we know the filters will have to be represented using the first order section and the second order section in order to avoid the here the sensitivity of the coefficients due to the parameter changes or due to the any environmental changes here. So these are the 7 steps that will be used in order to design the filter. We are again repeating this one. See, in order to design the filter, first the question is given here, that is the specification or the requirement is given. We can say this is the requirement, that is the question itself is a requirement that we have to design a digital filter using the Butterworth approximation. So what we have to do, we have to define these specifications, and then these specification has to be converted into the analog domain if they are described in the digital domain, right? And after that, the next step is to determine the order of the filter. And how the order of the filter will be determined, this formula will be different for the different types of the approximation, because we have derived this relation from where? See here, we have considered the Butterworth approximation. This is the Butterworth approximation here. This is the Butterworth approximation, and for the Butterworth approximation, the equation is given here. So from this equation, we have derived the how the n will be calculated. For the AP, that is the here we have replaced the omega by omega p. Then we have defined here the AP square, and similarly we have described here the AS square. Then by these two relations, that is if we consider the AP square upon the AS square, we can get here the value of the n, and the value of the n will be derived by this formula here, that is 0.5 log R1 by 2 log 10 to power 0.1 AS minus 1 divided by 10 to power 0.1 AP minus of the 1, then total divided by log omega S by omega P. This is the formula that has been derived for the in order to get the order of the filter using which type of the approximation? Butterworth approximation. Now this formula will be used in order to compute the order of the filter only when we are using the Butterworth approximation. Similarly, if we are using the Chebyshев 1 or the Chebyshef 2 approximation, then accordingly we have to derive the order, and then we will calculate the order of the filter here. And here, by putting the values of the AP, AS, omega P and omega S, we have calculated the value of the n, and that value of the n is 5.88. And since the order of the filter should be integer, so we will consider which value the next higher integer will be selected here, and that has become in this particular case is 6. And after getting the value of the order, the next step is to determine the omega c cutoff frequency, and from where we will determine the cutoff frequency. Again, we will move towards the approximation concept, and from that approximation we will derive the omega c. And we know the pass band edge frequency, stop band edge frequency, pass band attenuation, stop band attenuation, and also we have calculated the order, so we can calculate the cutoff frequency here. So in the first step, what we have done, we have specified the frequency into the analog domain. In the second step, order has been calculated. In the third step, cutoff frequency has been calculated, and in the fourth step, we are going to determine the transfer function of the corresponding roots of the corresponding order here. So what are the roots? Now the n is the 6. So here the value of the k will exist from 0 to n minus 1, that is the 0 to 5. So, and for each value of the k, we have to calculate the roots pk, and how the roots will be calculated. These roots are the omega defined as the omega c e to power j n plus 2k plus 1 multiplied by pi, then total divided by twice of n. And this has been derived again from where? From the approximation which we have utilized here. And what is the approximation? It is for the which type of the approximation? It is for the Butterworth approximation. So similarly, for the another type of the approximation, we will derive here how the roots will be calculated. So after getting here the roots here, we have to decide which roots will be considered in order to maintain the stability of the system here. So we will find here that in this particular case, we are getting the double roots than that of the required roots, because this is the concept of the HS as well as the H of the minus S. We have considered here the square of the magnitude square, HS square here. So we will consider only those roots which are lying towards the left half of the S plane. So because if the roots are lying only in the left half of the S plane, means these are the poles which are lying in the left half of the S plane, and helps the system will be stable or the filter will be stable. So we will select these roots or these poles here, and then after getting the roots, in the next step, that is the here the how the transfer function will be described here, how the system function of this filter in analog domain will be described. That will be described by omega c its power n divided by s minus s1, s minus its conjugate, then s minus s2, s minus s2 conjugate, and so on. And in this case, there are the three roots along with their conjugate here. So we will consider the s minus s1, s minus s1 star, that is the conjugate of that root, s minus s2, s minus s2 star are the conjugate, and s minus s3 and s minus s3 star here. Now we have to put here the values of the omega c, s1 and its complex conjugate, and then we have to solve the denominator as well as the numerator terms here. And finally, we will get a final transfer function, and that such transfer function is related to the transfer function of the filter which we have designed in the analog domain. I'm repeating it. It is a function of the S, and we are saying that this is a filter in the analog domain because we know that in the analog or in the continuous time domain, the systems are described with the help of the differential equation if we are in the time domain, and for the purpose of the transformation we use the Laplace transformation, and that function or that transfer function becomes the function of the S. And we are interested in order to design the filter in the digital domain. So what is the next step? Next step is to convert the designed filter from the analog domain to the digital domain. And for that purpose, we will use the different types of the transformation here, and we will utilize here, suppose bilinear transformation. Then according to the bilinear transformation, how the S will be transformed, we will put the values of the S, and then we will get here the Z, HZ, and then whatever is the SZ, that will be represented either in the cascade manner or in the parallel form, so that we can represent the architecture of our design filter either in the cascade form or in the parallel form. So this is the here the approach that is used in order to design the filter using the approach of the designing in the analog domain and then transforming it into the digital domain. And for that purpose, there are the four types of the approximation. One is the Butterworth approximation, the second one is the Chebyshev 1, Chebyshev 2, and the fourth one is the here the elliptic, or sometimes this is also known as the Power approximation. So when we select any particular type of the approximation, that what happens, we have to derive the transfer function on the basis of those approximations here, or we can also derive our own approximation depending upon the situations and the requirement here. So if we have design, and what is the approach? First of all, we will design the filter that is the low pass filter here. And after designing the low pass filter, suppose we are interested in order to design the another low pass filter having the another cutoff frequency, then for that purpose here the S will be replaced by the S by omega C, where the omega C is the new cutoff frequency. And if we are interested in order to design the high pass filter, then naturally the first filter will be designed in the for the low pass purposes, and then it will be transformed or by replacing the S by omega by C, omega by S, or the omega C by S here. And if we are interested in order to design the band pass filter from the low pass filter, then after designing the low pass filter, here the S will be replaced by S square plus omega 1 multiplied by omega 2 divided by S, and in bracket omega 2 minus omega 1. So these are the approaches, or these are the steps that will be utilized in order to design the filter in analog domain, and then the transforming it into the digital domain. And for that purpose, we have described here the steps, as well as we have also considered one example of the designing. So we have covered this portion also, that is how the IIR filter will be designed in analog domain, and then how it will be transformed into the digital domain. So far we have discussed the designing of the FIR filter using the windowing method, and we have also discussed here the designing of the IIR filter using the analog to digital conversion method. In this one, we will design the filter into the analog domain using any one type of the approximation, like the Butterworth Cebeshev 1, Cebeshev 2, or the elliptic approximation, and then that transfer function or that transfer function of the design filter will be transformed into the digital domain using the bilinear transformation or any other type of the transformation here. So this is about the today's discussion, and if you will have any doubt or the query, then please ask for it. Any query, please?